Today we're going to talk about the concept of electrical equivalence and use it to develop a new circuit analysis tool known as the source transformation. Now we've actually been talking about electrical equivalence all quarter, so let me explain myself. Consider the following simple circuit. Where we have an independent voltage source supplying some voltage Vs to a network that contains two resistors in series. Okay? This resistive network will have a voltage drop over it, which I'm going to call VL, a current flowing through it, which I'm going to call IL, and the product of those two quantities, VL and IL, represent the power that is absorbed by this resistive network. So we could easily see that the quantity VL is equal to the voltage drop over resistor R1, which is going to be IL times the resistor R1, and the voltage drop over the resistor R2, which is going to be IL times the resistor R2, and that would give us IL times R1 plus R2. We could use Ohm's law to find that IL is simply Vs divided by the total series resistance, which in this case is R1 plus R2. Now, from the perspective of this voltage source Vs, we could redraw this circuit as an electrical equivalent circuit containing an equivalent resistance, Req. So we have our exact same voltage source, but instead we're going to connect a single resistor, Req, where Req is simply the sum of R1 plus R2. We're going to define our voltage VL in the same way. It's the voltage drop over the resistive network. The current IL is the current flowing through the resistive network. And we can see that VL is IL times Req, which is IL times R1 plus R2. And we can see that IL is Vs divided by Req, which is simply Vs divided by R1 plus R2. So the resistive network of two resistors in series has an electrical equivalent of a single resistance. And this is what we visited when we talked about resistor combination techniques. We could work a similar example with parallel resistors, but we already know what the result of that is going to be. We could work an example where, looking from the perspective of the resistor with multiple voltage sources, we could develop the rules for source combination of voltage sources. Or from the point of a resistor, we could look at a network that had current sources in parallel and develop relationships in order to be able to combine those parallel current sources into a single equivalent current source, which we've all done before. So we have been working with the concept of electrical equivalence actually for quite some time in this class. One of the key caveats of electrical equivalence is that the voltage drop and the current through the electrically equivalent network and the original network must be exactly the same. We are going to show today that the following two networks are electrically equivalent. So, our first network is what we are going to call a practical voltage source, and we'll talk about that in detail momentarily. And our other network is going to be a practical current source. And we will also talk about this guy in detail. And we are going to learn what I will call a bilateral transformation between these two forms. Okay? So we're going to prove today, using the concept of electrical equivalence, that under very certain conditions, we could actually replace a practical voltage source, which contains an independent voltage source in series with some resistance, by an electrically equivalent practical current source, which contains an independent current source in parallel with some resistance. And then we can use this transformation to simplify circuits and aid in our circuit analysis. So let's start by talking about independent voltage sources, ideal independent voltage sources actually, under load. So let's say that we have a voltage source Vs and it's an independent voltage source, so we know that the difference in electric potential between this terminal and this terminal is exactly Vs, and we connect it to what I'm going to call a load resistance RL, where we will observe some voltage drop VL over our load and some current IL flowing through our load. And this current IL is what's being supplied by our voltage source Vs. So we can easily figure out what's going on here just using Ohm's law, right? In a general case, IL will be Vs divided by RL, and VL will simply be Vs. But there's actually one value of resistance for this guy RL that causes those relationships to mess up. And that relationship is when RL is equal to 0. So if RL is equal to 0, IL approaches infinity, which is a problem, and we could see VL should also be equal to IL times RL. So we would have a case where we are effectively setting Vs, which has some fixed value, is also at the same time equal to 0. And so that's a problem because our circuit theory techniques have broken down. Okay. The reason they've broken down is because we have an unrealizable situation. Even if we had the most efficient electrical grid on the planet, it would be impossible for our electrical grid and the utilities to provide an infinite amount of current. Cannot ever happen, right? It's beyond the bounds of physics. So in practice, a real voltage source, or a practical voltage source, contains an internal source resistance whose role is to limit the current. So if we had a practical voltage source, Vs in series with some source resistance Rs. Now, our current will never actually be able to go to zero. And we can prove it very simply. If I short circuit my practical voltage source, this is going to cause the maximum possible amount of current to flow in my practical voltage source. I would see that this current IL max is simply Vs divided by the source resistance Rs. So we're no longer capable of getting an analysis result that gives us infinity. So this is a very, very good approximation of how a real voltage source behaves. Take, for instance, your 9-volt battery pack that you used in your engineering 120 class. You were warned on the first several days of class before you soldered a barrel jack to the terminals of your battery pack to never leave the batteries in the battery pack while it was sitting in your bag with the rest of the parts of your kit. And the reason that you were warned for this is because if you accidentally short-circuited the battery pack, it couldn't produce an infinite amount of current, but it could produce a large enough amount of current to actually melt your battery pack and things like that, because the internal resistance of the battery would be generating that large current and transforming it into heat. Now let's take a moment to look at current sources under load. So for a current source under load, where we have some ideal independent current source IS connected to some load resistance RL, we'll define our voltage drop over our load to be VL here, and the current flowing through our load to be IL, like so. So this is an independent current source, which means the current flowing through this branch is IS, regardless of whatever voltage appears over its terminals. So we can write some simple equations again. The voltage drop over our load resistor VL is simply IS times RL. The current flowing through our load is going to be simply VL divided by RL, which should be exactly equal to our current IS. Okay. Now there's a particular value of resistor RL that makes this also behave extremely awkwardly. When RL is equal to infinity, so when we replace this RL with an open circuit, we see that VL goes to infinity, which means IL must be going to 0. So again, we're having some quantity approach infinity. It's a voltage. Since voltage is defined as the amount of work per unit charge needed to move 1 coulomb of energy between 2 points in a circuit, this implies that we are generating an infinite transfer of energy, which is impossible. Another thing is that if IL is 0, no current should be able to flow through the open circuit. It can't also be equal to IS at the same time. Effectively, in a real situation, we observe something like this whenever we see arcing come out of our outlets. Say we unplug a hairdryer or something like that while it's still on, and we see sparks. Those sparks are the current source generating so much energy that it's ionizing the air particles between the two terminals and being able to send electricity for a short amount of time. Okay, it's typically speaking, it's quite a bad situation. Spark gaps and things like that can be used for old-timey communication purposes, but generally speaking, you're not trying to start fires with your electricity, so generating such large voltages that cause ionization of the air is a bad thing. Now we can rectify this situation by, again, using a resistor to limit the amount of voltage that can be produced by our current source. But in this case, we're going to have to put the resistor in parallel with the current source, because if we put the resistor in series, we could still see an open circuit resistance of infinity that would cause us issues. So our practical current source which contains an ideal current source IS in parallel with an internal resistance RS, the maximum voltage that it could ever generate would be when it's connected to an open circuit or an infinite resistance, right? Because if we put any resistance that wasn't infinity in parallel with this guy, the total equivalent resistance is going to be smaller than RS by itself, which means that current would flow through that smaller equivalent resistance and generate a smaller voltage. So the maximum voltage, VL max, that can possibly be seen by our practical current source is simply IS times RS, which is never going to be infinity. So we've limited the amount of voltage. We now have accounted for and circumvented the infinite transfer of energy that we have. So now that we've discussed what practical voltage sources and what practical current sources are, let's talk about how and under what conditions they are electrically equivalent. So for a practical voltage source, where we have some voltage Vs in series with some resistance Rs, let's load this with a load resistor RL. And determine the load voltage VL and the load current IL. So to determine the load voltage VL, I'm going to use voltage division because I have a known voltage that's being dropped over two resistors in series. So I can see pretty easily that VL is simply equal to VS multiplied by RL divided by RS plus RL, or VS RL divided by RS plus RL. I can see that my load current IL is simply VS divided by RS plus RL. Now, let's look at a practical current source under load. Here's my load voltage VL, my load current IL. So our load voltage VL, this current source sees two resistors in parallel. So VL would simply be IS times the equivalent resistance of those guys in parallel, which is going to be IS times RS RL divided by RS plus RL. And our load current, IL, we can get using current division, where we would have IS multiplied by 1 over RL divided by 1 over RS plus 1 over RL, which is identical to IS times RS divided by RS plus RL. So if these two circuits are electrically equivalent, under what conditions is that true? Well, if we look at the voltages, we can see that if Vs is equal to Is times Rs, then this expression for VL and this expression for VL are exactly the same. And if we look at our current relationships, if Vs is equal to Is times Rs, then the IL for our parallel current source and the for our practical current source and the IL for our practical voltage source are the same. So this gives us then the simple relationship that these guys are electrically equivalent when Vs is equal to Is times Rs. So under that specific condition, I can replace, from the perspective of a load resistor, a practical voltage source with a practical current source and lose no information whatsoever. So let's use that concept to analyze a circuit. So our circuit in question will be this one, which I found on Dr. Ravel Ammerman's YouTube channel. And I think it's probably one of the best example problems for source transformation that you could come across. Because it's really got all of the nuances of the operation of source transformation buried inside of it. And our goal in analyzing this circuit is to determine this current, Ix, that's flowing through our 1.5 ohm resistor on the right. Oh, excuse me. And this is a 34 volt voltage source. So I'd like to talk for a moment about why circuit analysis, source transformation would be a wonderful circuit analysis tool in this particular problem. Because we've already learned nodal analysis and we've already learned mesh analysis, and your instinct might be to just use nodal or mesh to solve for that quantity Ix. And there's nothing remotely wrong with that, okay? But if we look, there are 1, 2, 3, 4 meshes, okay? So we would have to set up a system of equations with 4 unknowns and then solve that system simultaneously. If we were using mesh analysis, if we use nodal analysis, we have this bottom common node. So that's 1, 2, 3, 4, and 5 nodes total. One of them would be set to ground, or our reference. So we would still be having to set up a system of equations that have 4 unknowns and solving them simultaneously. Now, to me personally, the calculator that I use most frequently can't do that. So I would have to rely on getting out my computer and using MathCAD, which there's nothing wrong with that per se, but it's not always the most inconvenient means. Another thing is that if I have to set up 4 equations, that's 4 opportunities for me to make simple mistakes. So to avoid that, we could actually use source transformation, where we're really going to break this guy up into digestible bites and make it look much, much more simple. So the first thing that we're going to do is identify our practical sources, okay? So I have a 2 amp source in parallel with a 6 ohm resistor, so this forms a practical current source. And I am going to draw a pair of terminals. It's effectively trying to show where that practical current source is connected to the circuit, okay? I also have a practical voltage source here, a 17 ohm resistor in series with a 34 volt source makes a practical voltage source. And this 5 ohm resistor and this 1 amp source form a practical current source as well. So there are 3 practical sources that I could perform transformations on here in order to simplify the circuit. So let's look at the 2 amp source in parallel with the 6 ohm resistor. Two amps in parallel with 6 ohms using the relationship Vs is equal to Is times Rs means that its electrical equivalent would be a practical voltage source where we would have 2 amps times 6 ohms is 12 volts in series with that same 6 ohm resistor. I want to point something out real quick. If the arrow is directed up, the positive polarity of terminal of the voltage source should be on top. If the arrow were directed down, the positive polarity terminal of the voltage source should be on bottom. So we could replace that 2 amp, 6 ohm practical current source with this 12 volt, 6 ohm practical voltage source. But let's look at the other practical current source as well. So we have a 1 amp source in parallel with a 5 ohm resistor. And so I'm going to posit that we could convert this to a voltage source in series with our 5 ohm resistor, where the voltage source is going to be 1 amps times 5 ohms is 5 volts. And because the head of the arrow is on the right, the positive polarity terminal of the voltage source should be on the right. So I'm going to disconnect this practical current source from those terminals that I drew and replace it with its electrical equivalent. And I'm going to disconnect this practical source and replace it with its electrical equivalent. Notice that in 2 very simple changes, I have gone from having 4 meshes to 2. Vastly simplifying things. But also notice I have a 6 ohm resistor in series with a 6 ohm resistor in series with a 5 ohm resistor. So I could replace these 3 resistors with one. 6 plus 6 is 12 plus 5 is 17. So I could replace these 3 resistors with a 17 ohm resistor. And I could replace this 12 volt source in series with this 5 volt source with a 17 volt source. So I'm going to go ahead and do that. I'm just using source combination techniques for voltage sources in series and resistor combination techniques for resistors in series. So 5 plus 6 is 17. (12 plus 5 was also 17. And so this is a significantly simplified representation of the circuit that we had. But we could actually simplify it further, because if you'll notice, I now have a practical voltage source containing a 17 volt source and a 17 ohm resistor in parallel with a practical voltage source containing a 17 ohm resistor and a 34 volt source. So I can do transformations on my practical voltage sources now, where (17 volts in series with 17 ohms, again using the relationship Vs is equal to Is times Rs, has an electrical equivalent of 17 volts divided by 17 ohms is 1 amp, where since my positive polarity terminal is on top, my arrow needs to be pointed up in parallel with a 17 ohm resistor. And here I have a 17 ohm resistor, negative plus 34 volt source. So this has an electrical equivalent of 34 divided by 17, gives me 2. Since the positive polarity terminal is on bottom, my arrow will be down. 17. And I'm going to draw my terminals slightly different for this one so that they match the way that I presented them. So I'm going to put one on the top like this and one on the bottom like this, but we could really just extend them off to the right like I've done before, but it'll make it easier to drop into this circuit. So I'm going to replace both of my practical voltage sources with their practical current source equivalents. So let's start with that guy in the middle. Two amps down. $17 ohms. And then we have our 17 ohm resistor in parallel. That's getting very crooked. With our 1 amp source directed up. Now, we have this node on the top, and we have this node on the bottom, so we have a single node pair circuit where I see that I have a 1 amp source in parallel with a 2 amp source, so I could replace that with a 1 amp source direction down. So 2 amps down minus 1 amp up gives us 1 amp down. I have a 17 ohm resistor in parallel with a 17 ohm resistor. So that's going to give me, let's see, 17 over 2 is 8.5. And now I can see that my current of interest, Ix, using current division, is simply negative 1 amp times 1 over 1.5 ohms divided by 1 over 8.5 ohms plus 1 over 1.5 ohms, which, let me grab my calculator real quick. Negative 1 times 1 over 1.5, 1 over 8.5 plus 1 over 1.5 gives us negative 0.85 amperes. And we could have gotten that same result by doing one more source transformation where we would have had, let's just see. So I have a 1 amp source in parallel with an 8.5 ohm resistor. So that would give me positive polarity on bottom, negative polarity on top, 8.5 volts in series with that 8.5 ohm resistor in series with that 1.5 ohm source, or excuse me, 1.5 ohm resistor, where this is our current Ix that we're trying to define. And using Ohm's law, Ix would have been negative 8.5 volts divided by 10 ohms. The total resistance is negative 0.85 amps. So we got the same result either way. So hopefully this example illustrates how powerful the concept of source transformation can be. We took a circuit that had 4 meshes or 5 nodes, and we were able to make it look like a single node pair circuit and with one more transformation, a single loop circuit without doing any complicated math really whatsoever. So to me, that makes this a very, very powerful and very useful tool. The next topic that we're going to talk about today is what's called the maximum power transfer theorem. Transfer theorem. Okay. And we're going to look at this using a practical voltage source as our example. That being said, we could just as easily use a practical current source. So let's say that we have a practical voltage source, Vs, in series with some resistance Rs, and our practical voltage source is loaded by some load resistance RL. The voltage drop over the load will be VL. The current flowing through the load will be IL, where VL is equal to Vs RL over Rs plus RL using voltage division, and our current IL is equal to Vs divided by Rs plus RL. The power absorbed by our load resistor, PL, is VL multiplied by IL. So that's going to give me Vs squared times RL divided by the quantity Rs plus RL squared. Okay. So what if we wanted to know the maximum amount of power that that practical voltage source could supply to a well-chosen load resistor? Well, if we plotted the power as a function of the value of RL, where our power measured in watts is on the y-axis, and RL, measured in ohms, is on the x-axis, our graph is going to look something like this. Where this value represents the maximum power transferred, and we want to know what value of RL makes that happen. Okay? We can do that by taking the derivative of PL with respect to RL and setting it equal to 0. So the derivative of PL with respect to RL, and I'm going to have to look at my notes for this one. I don't have it off the top of my head, is Rs plus RL squared Vs squared minus Vs squared multiplied by a factor of 2 multiplied by RL multiplied by RS plus RL, and this whole denominator is divided by RS plus RL to the fourth power, and we want this to go to 0 in order to determine the maximum value. So for this to go to 0, only the numerator needs to actually go to 0. So we could see that RS plus RL quantity squared, VS squared minus VS squared times 2RL RS plus RL needs to equal 0. Notice there's a common factor of VS squared on both terms. So this is this quantity multiplied by VS squared, and this is this quantity multiplied by VS squared. So we can divide both sides by VS squared to get rid of that. So now we have RS plus RL squared minus 2RL RS plus RL. Well, there's a common factor of RS plus RL on both sides. So that means that RS plus RL minus twice RL needs to be 0. And we can easily solve this and find that maximum power transfer will occur when RL is exactly equal to RS. So, for our practical voltage source representation, PL max occurs when RL is equal to RS, okay? So that means if we look in this equation right here, we're going to have VS squared times RS divided by twice RS squared. So that's VS squared RS divided by 4 RS squared. And we can factor out this common factor of RS, and this is our result for a practical voltage source. VS squared divided by 4 RS. If instead we had a practical current source, or we could really just use Ohm's law here, we could find that this is exactly equal to 1/4 IS squared times RS. So let's work an example to put this into practice. So our goal is to find out the maximum power that could be transferred to a well-chosen value of RL. So when this RL is the exact same as the source resistance of the equivalent circuit, electrically equivalent circuit of everything that's connected to it, maximum power transfer will occur. So we can see right off the bat that we do not have a practical voltage source or a practical current source, so we cannot just directly apply the equations that we just derived. Instead, we're going to have to use our source transformation techniques that we learned earlier in order to simplify this. So, for example, I have a 20 volt source in series with a 12 ohm resistor, which means I can replace this with a 20/12 amp source, direction up. In parallel with a 12 ohm resistor, which puts my 12 ohm resistor in series with my 8 ohm resistor. So that would be 12 times 8 over 12 plus 8, which is a 4.8 ohm resistor. Now, I'm going to go ahead and transform this back into a practical voltage source. So that's 20/12 times 4.8 gives me an 8 volt source. In series with a 4.8 ohm resistor. Over here on the right-hand side, I have a 6 ohm resistor in parallel with a 2 amp source. So that's going to look like 6 times 2 is 12. So 12 volts. The arrow is pointed down. So positive polarity terminal on bottom puts my 6 ohm resistor here. Now I can see that I have an 8 volt source in series with a 12 volt source, and they have the same polarity. If I followed my current clockwise, I would see the negative polarity terminal first. So I can combine them together to form 8 plus 12 is 20 volts. I have 5 plus 6 is 11 plus 4.8 ohms. So that is 15.8. And that's connected to my load resistance, RL. So the maximum power that could be transferred by this original circuit to a load resistance RL is PL max is equal to 20 volts quantity squared divided by 4 times 15.8 ohms. 20 squared divided by 4 times 15.8, 6.329 watts. So in this example, we've reinforced our source transformation techniques and used them to simplify a circuit down to a practical source connected to a load, which allows us to use our maximum power transfer theorem to determine the maximum power that could be provided to this load resistor RL under the condition that it was the same as this 15.8 ohm resistor.